again, it's too long, right? Oh, did I say what did I say? That's
That
not
was
36
next one.
degrees. So we're gonna rotate around the point. What did I say? 364 went around more than, okay, so, so now I wanna get this point of intersection here and here. And then hide this, hide that, and we really need to see those. And then draw this line segment here, and this line segment here. And now if we measure this angle, which way did we go around? Like this? No, wrong side. Just like this. Yeah, so that's a right angle also, right? And you can measure this angle here, I think. I'm not sure which way to do this. Right, so that's going to be the complement of 36 degrees, which is 54 degrees there. Can you see that all right? So we've got this circle. Move over here. Can we just move the whole circle? Yeah. Oh, move the whole thing, huh? Move this circle. Move it over there. Another circle? We need 3 of these, huh? All right. And so I'm going to again draw a ray
That's what I thought I heard.
through the center. How's that? Oh, okay, so there's that point, right? So I'm going to not show that. Draw the segment from there to there. And what's the angle I want to rotate now? 59, 51, 20. Okay. I have to work out what that is as a decimal, huh? So I guess I could get a new page and say 51 divided by 60 plus 20 divided by 3600. And that would give me 0.85 repeat. Okay. So I'm going to rotate this around this point here by 59.85555555, and I want to find the point of intersection of this and that. Okay, and I guess I want to not see this. Okay, and just draw this line segment here. And should we again verify that that's a right angle? Doesn't hurt. Oh, wrong side. Crap. Keep forgetting which way to go. Can I just undo that? Okay, and then on this side. Okay, we'll see. Yeah, it says, yeah, that's also a right angle. And then what's the complementary angle? I think I go this way for that, right? That's 36 and some degrees. And can we bring that out here, the measurement? Yeah, so this is 31, this is 54, this is 77.86. And so what do they want us to do? Jeez. Okay, so this is task 14. Ptolemy proposes to take the 3 right-angled triangles out of the diagram in each case and inscribe them in a circle. In general, if PQR is a right-angled triangle with right-angle Q, use the result quoted about the measure of inscribed angles. Explain why it must be that a circle in which the triangle inscribed must have a center 0 at the midpoint of the hypotenuse. Right. Well, that seems obvious now, right? That if you circumscribe the circle around a right triangle, then the hypotenuse is diameter of the circle, which is twice the radius, and so the center point bisects the hypotenuse. Part B, now suppose that triangle KEG is describe why the arc GK is 24, 17, 20. Oh, KEG, huh? So which one is K and which one is E and which one is G? Well, K is at the larger angle? Okay, so let's label this, this point here is going to be K. And, so, which point is the right angle? That's G, huh? So I can label this point up here G, and I can label this point over here E, and then I can see what's what and answer their question. What was the question again? So this is 12.14, hard to read there. It was explain why GK has a degree measure of 24 degrees. Okay, so what's GK? Oh, that's this angle here. Sorry, the line segment GK. Oh, well, that's obvious now, right? Because the central angle is twice the circular angle, right? So if I were to connect this point with that point, then the so this is G, this is K, this is E, and this angle must be twice that, so it's 24 degrees, 17 minutes and 20 seconds. See what I did there? Twice 18 minutes is 16, but twice 40 would be 80 seconds. 80 seconds is 1 minute, it's 20 seconds, right? So I took one of those and one of those minutes and added it to the minutes place. So now we want to convert that we want to say what is the degree measure of that arc. So how do we get that arc? Sorry, that chord. So remind me again what I'm doing.
GK?
Yeah. We want to show that, explain why arc GK. Oh, well, arc GK, that's easy, right? Arc GK is equal to angle GOK, and that's equal to twice angle GEK. Sorry, twice angle GEK. And so that's going to be equal to 24 degrees, 17 minutes, and 20 seconds. Is that what they wanted us to show? Yeah, okay. So the same thing with GE. I'm sorry. GE is going to be, okay, so let's see, this angle here is 12 degrees, 8 minutes, and 40 seconds. So this would also be that same angle, right? Because they're, it's an isosceles triangle. The GEO is isosceles, right? So what is GE? So arc GE is equal to angle, the central angle measures the arc, right? So that's going to be angle GOE. And that's going to be 180 minus 24, 17, 20, right? And what do you get here? Well, you take the 24 away, and that's going to be 156, but then we need to take one of those away so we can subtract 60 minutes minus 17 minutes and get 43 minutes, and we'll write 42 minutes so we can take one of those minutes and convert it to 60 seconds, and subtract the 20 seconds from the 60 seconds, we get 40 seconds. And is that what we wanted to show? Yeah, sure enough. Okay, as Ptolemy indicates. Similarly, verifying the corresponding measures of the arc to the Ptolemy reports for the circles that subscribe ZEG and NEG. Okay, well, we've seen how to do it for this one, so we'll say that we know how and move on. So in the middle sentence of the last excerpt, Ptolemy consults his own table of chords and updated a much more extensive table than the one produced by Hipparchus 300 years earlier. As did Hipparchus, according to the reconstruction we proposed. Ptolemy tabulated the measures of arcs in degrees and the corresponding measures of chords that span those arcs within a certain reference circle. But Ptolemy's table was far more extensive. He recorded chords for every arc from 0 to 180 degrees in steps of half a degree. Ah, okay, so that's a lot finer. Moreover, while Hipparchus measured his chords in units of arc minutes, Ptolemy did not. He chose the reference circle to have radius of unit length and subdivided sexagesimal